O Telescópio Espacial James Webb tem como missão desvendar os segredos do cosmos.
Think about it as a telescope that enables us to see the hidden universe.
Em busca dos pilares químicos da vida para além do planeta Terra.
Is there life on an Earth-like planet around a sun-like star? Is there an Earth 2.0 out there?
Procurando pistas para desvendar o mistério dos buracos negros.
Where do they start growing? How bright do they get?
E investigando a nossa história cósmica mais a fundo do que alguma vez foi possível.
We are reaching back to what we think is the first epoch of galaxies.
That one's interesting.
And we've only just started. That's the craziest thing, right?
Novo olhar sobre o universo começa agora.
This telescope was designed to answer some of the biggest questions in astronomy today. Everything from detecting the very first galaxies that were born after the Big Bang to looking at objects within our own solar system and everything in space and time in between.
We're trying to tell the whole human story from the beginning of the Big Bang right up to did life emerge on another Earth-like planet around another star like our sun? And that's a massive story.
But I'm also, got my ears pricked up for what are we going to learn that we didn't even know we were supposed to be looking for.
O Telescópio Espacial James Webb, também conhecido por JWST, é o maior e mais complexo telescópio espacial alguma vez construído. Assolado por percalços e derrapagens de custos, demorou décadas a ser concluído.
We got to the point where we started thinking, is this thing ever going to fly, right? Is it too complicated?
Foi finalmente lançado a 25 de dezembro de 2021.
This will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
JWST is an example of what people can do on a large scale. 20,000 people around the world contributed to making this telescope exist.
Agora, os investigadores vão testar o seu novo telescópio.
Methane's always been a mystery, right? This is like our new souped-up convertible that we want to take out for many spins, multiple spins, and really test its limits.
Just look at that.
There's a period where you have to feel it out. You've got to learn how to use it, and that's what we're doing.
We had some idea what we might be going to see in this galaxy.
So we're trying to really get up to speed so that we're not just driving the car, but we're really learning how do you take the corners the best? How do we optimize what we're doing here?
Esta é a história dos momentos altos e baixos da exploração do cosmos com um telescópio totalmente novo.
We're kind of the guinea pigs to show how this all works. It took me a while to figure it out, but it's actually
Levando-o aos limites. No seu primeiríssimo capítulo de exploração, os investigadores estão a descobrir o que lhes pode revelar o seu novo olho sobre o universo. A 12 de julho de 2022, o mundo pôde finalmente ver as primeiras imagens do JWST.
I was flabbergasted, right? It was better than I could have imagined. I knew they were going to be good, but I didn't think they were going to be that good.
The thing that struck me was the amount of detail we were seeing in these images.
It's sort of like putting glasses on for the first time. Everything is just like crystal clear, and there's just so much to see.
I guess my reaction was just a total sense of wonderment. It's like sort of that feeling when you were a kid and you look up at the night sky and you just look out into the universe and you see all these stars and you wonder how big is the universe and when did it all start? I felt that looking at those images. I just felt that sense of wonderment.
À medida que vão chegando os primeiros lotes de dados e de imagens, os cientistas procuram novas pistas para responder a algumas das nossas mais profundas perguntas.
I study galaxies in my own research, and so I am really excited to see what that first epoch of galaxies to form after the Big Bang, to see what those galaxies are like. But if I'm being honest, I think the most important question we have in astronomy, or maybe even as a species, is there life out there?
Are we alone is definitely one of the key questions that I would love to answer.
For me, that is such an earth-shattering idea that by itself would be worth the entire telescope.
There are over 5,000 exoplanets that have been discovered so far. The actual number changes every day, so even I can't keep track.
Os exoplanetas são planetas alienígenas que existem para além do nosso sistema solar.
But it really does blow the mind when you think about Carl Sagan saying there were billions of galaxies. And so that begs the question, are there trillions of exoplanets in the universe? I think there are.
Para termos ideia do que isto significa, a nossa galáxia, a Via Láctea, contém pelo menos 100 mil milhões de estrelas, e os astrónomos estimam que poderá albergar milhares de sistemas solares com planetas muito semelhantes ao nosso. A grande pergunta é: algum deles contra a vida?
The odds that one of these planets has the ingredients for life are very high.
Are we alone in the universe, right? All common sense of looking at how biology, chemistry, geology, and physics work would say, no, we're not alone.
Durante as últimas décadas, os nossos telescópios mais potentes têm procurado a existência de vida, tal como a conhecemos. Mas apenas encontrar esses mundos distantes é desde logo uma tarefa gigantesca.
As we're looking at planets within our galaxy, but outside of the solar system, the first thing we need to remember is they're really, really small.
Estão também a anos-luz de distância e ocultos pelo brilho da estrela que orbitam.
You can imagine, it's really hard to find something faint in the glare of that really bright star.
I've often heard detecting exoplanets as like looking for a firefly in front of a lighthouse. But I might argue that it's actually more challenging.
So astronomers have been very creative and they have come up with techniques that basically look at the planet when they pass in front of the star.
So just waiting patiently, looking at the stars, such that you see a little dimming in the light because the planet blocks a little bit of that light.
Uma minúscula diminuição da luminosidade pode revelar a presença de um planeta. E quando a luz estelar atravessa a atmosfera do planeta, os instrumentos do JWST procuram indícios químicos acerca da composição desse planeta alienígena.
There are two types of science instruments in general: cameras that produce images and spectroscopes that produce spectra, rainbows. And the public is always fascinated and awed by the images that come. And the images hold a wealth of scientific data. But arguably the workhorse of scientific instruments is the spectroscope.
Para demonstrar o que revela um espectroscópio, Matthew Diaz construiu uma versão de mesa enquanto estagiava no JWST. Usa uma lanterna para simular a luz de um corpo celeste. A luz passa por uma lente muito semelhante à lente de uma câmara tradicional.
And it focuses all the light to one point. There's this little slit here that allows the light to pass through.
A seguir, a luz passa por outra lente e depois por um prisma.
What the prism is doing is it's splitting the light into colors, and that is how you get your spectrum.
It's the same as if you see a rainbow. The light is actually being broken apart in such a way that you can see distinct colors.
E este espectro de luz está repleto de informação.
Each molecule has their own fingerprint, just like you have a fingerprint, like I have a fingerprint that's distinguishable. So we're looking for these key fingerprints of different molecules.
O que distingue um espectro de outro são falhas, onde átomos e moléculas revelam as suas identidades absorvendo luz.
Molecules in space on stars, in planets, can absorb certain colors of light. They just take that light out of the rainbow.
So you look for the pattern of lines to say, that's the barcode of calcium. That's the barcode of sodium.
They're fingerprints. They're like little signs with a little placard saying, hello, I'm hydrogen. Hi, I'm oxygen.
Os espectroscópios do JWST foram especialmente concebidos para detectar essas impressões digitais na faixa infravermelha do espectro.
So this is where we have signatures of key molecules that we want to look at in space, like water, carbon monoxide, carbon dioxide, methane. These are really key ingredients, essential for a habitable world or, what we would associate with life.
Os investigadores de exoplanetas iniciam a sua busca por estes ingredientes-chave, explorando a atmosfera de um gigante gasoso a 700 anos-luz de distância. O WASP-39b é maior do que Júpiter e imensamente maior do que a Terra.
It's larger than Jupiter, but it's a lot less dense than Jupiter.
Isso torna a sua atmosfera maior, mais leve e mais fácil de detectar.
We had studied WASP-39 with the Hubble Space Telescope. We had detected water vapor in its atmosphere already. And so we wanted to study this planet at new wavelengths using new instruments with a new telescope to see if we could get a bigger, broader picture of the planet.
O seu objetivo: descobrir se os espectroscópios do Webb conseguem detectar uma molécula nunca antes detectada na atmosfera de um exoplaneta. Uma molécula crítica para a vida, tal como a conhecemos, o CO2, dióxido de carbono. Na Terra, pode ser gerado por processos geológicos e é um composto essencial para a vida vegetal. Quando finalmente chegam os resultados,
So that big peak right there, that's all carbon dioxide?
Yes.
Yeah, that's beautiful.
We saw this giant carbon dioxide feature that just popped out right away in the data.
This carbon dioxide detection is just amazing.
We all had high fives. It was a big moment, like, wow, we can look at the carbon chemistry of these planets in detail.
And it just brought a big smile to my face. I was like, yes, we did it.
There are definitely some other bumps in there, right, that we don't quite...
o espectro revelou também uma surpresa. A primeira detecção de dióxido de enxofre num planeta fora do nosso sistema solar. O dióxido de enxofre existe na camada de ozono da Terra, uma parte crucial da nossa atmosfera que nos protege da nociva radiação ultravioleta do Sol. A presença destas moléculas na atmosfera do planeta WASP-39b é uma descoberta histórica.
What we've learned with JWST so far is that the data it's providing are exquisite for exoplanet atmospheres. And that has everybody salivating for more. More spectra, more transits.
A próxima grande pergunta é: conseguirá o JWST detectar uma atmosfera num planeta rochoso muito menor, de tamanho semelhante ao da Terra? Uma coisa é certa: não será fácil.
We've never even detected an atmosphere around a rocky planet before. So now, with JWST, we have our very, very first chance to do that on a very select few planets.
Daqui a alguns meses terão a sua primeira observação de um mundo rochoso e irão ver se conseguem detectar uma atmosfera.
Being able to perhaps make the first detections of an atmosphere on planets as small as the Earth is something that you only have dreamed of so far.
O JWST procura também os pilares químicos da vida, muito mais perto de casa, no nosso quintal cósmico.
One big question I want this telescope to answer is if there is life in our own solar system. If we found it in our own solar system, it would really hit home that it's not so rare that life can happen.
There are 3 places
in our solar system, beyond the Earth and beyond Mars, which are good candidates to go look for life. And those are Europa, around Jupiter, and the moons of Saturn, Enceladus and Titan.
Titan is a really exciting moon because it has an atmosphere and rivers and streams and lakes and oceans, but instead of being made of water like they are on Earth, they're made of methane, like liquid methane. So it has like a water cycle like we have on Earth, but it's a methane cycle. And that's really exciting for scientists because if we find life on Titan, it's not going to be life like it is on Earth. It's going to be totally different life. So that's a really exciting thing to be looking for, but also how do you look for life that you don't understand? So it's also a massive challenge.
So the question comes up, can life evolve from chemistry in a liquid medium that's not water, that doesn't have the polar properties of water? And the answer is we don't know.
Os investigadores procuram também os ingredientes da vida tal como a conhecemos em Encélado, uma lua de Saturno, e em Europa, uma lua de Júpiter.
Those are what are called ocean worlds, which means that they have liquid water in their interiors.
Imagine that there is a big body of water below the surface, protected from the environment.
Where there could be this subsurface ocean, where there could be hydrothermal vents, just like the ones that we have on Earth, which have life like plants and animals.
Full of organics, maybe some energy, internal energy, heat energy, and you have the soup of life. We don't know what could be happening there, but it's definitely a place that has all the right conditions for us to explore.
Some biochemists have suggested that it's in environments like this where life might have got going billions of years ago on the Earth.
And that would be amazing to find. Even if we just found bacteria, that would be amazing.
Em 2015, a missão Cassini estudou Saturno, os seus anéis e luas, e capturou esta imagem de plumas irrompendo do gelo no Polo Sul de Encélado.
We saw dozens of fine jets shooting off the south pole of Enceladus. When these pictures hit the web exploded.
And so we see with Enceladus, there are places where the ocean actually escapes from the surface and it just flows out of these cracks and bursts out into outer space.
So this is, in effect, our best opportunity to study an extraterrestrial habitable zone.
É possível que o mesmo se aplique à Europa, lua de Júpiter, coberta de fendas e sulcos, que podem ter sido causados pelo calor de um oceano situado abaixo da sua superfície gelada.
So we'll be looking for water signatures, so H2O, the same water that we have on Earth, and we'll also be looking for things like methane, which can be a chemical tracer that gives us an inclination that there might be something alive. Bacteria on Earth produces methane. We probably won't directly image life because you can't really image bacteria from a telescope, but you can look at what the bacteria creates.
Apesar da equipa ter agora de aguardar vários meses pela chegada das suas observações, o JWST continua a enviar para casa imagens impressionantes, como esta de Júpiter.
You can see the rings, you can see the moons. I mean, this is amazing. And not only that you can see those images, but you know you can actually explore those elements with incredible precision. You can see what they're made of, with the composition, the ices, the molecules in them.
When I first saw the image, I didn't even think I was looking at Neptune. I thought I was looking at a totally different planet. Seeing the rings in that much detail was just mind-blowing.
The last time we had seen that complete ring system was more than 30 years ago when the Voyager 2 spacecraft had flown over Neptune. So what we are going to be doing is looking very carefully at the ring system today, looking at how that ring system may have evolved with time over those intervening decades, and trying to understand what that tells us about ring systems in general. How long do they last? What's driving them?
When you have a new telescope and you're just getting new data, it is very much like being, a child around the holidays and you come downstairs and you're like, oh, what presents are going to be there? Every time you get this new image, it's just like unwrapping a present to basically see what there is to see. So it's a pretty exciting experience.
Mas antes de as podermos apreciar, estas fascinantes imagens têm de ser ajustadas.
The human eyes can only see a very narrow part of the spectrum, your blue to red, but there's light on either of the other sides of that spectrum. And of course, JWST is infrared, so it's on the red side of light.
Right, so Webb is an infrared telescope, so it's sensitive to light that is beyond what our eyes can see. So that's two layers of adjustments to just...
O trabalho do processador de dados de imagem, parte cientista, parte artista, é pegar nesta luz infravermelha invisível e traduzi-la para cores que os nossos olhos consigam ver. O JWST capta várias imagens do mesmo objeto celeste usando diferentes filtros de infravermelhos, representadas aqui a preto e branco.
We've taken light of different infrared wavelengths and split it up. And so there's long wavelength infrared, medium wavelengths, a little bit shorter, and then shorter wavelengths.
Agora, essas ondas de infravermelhos são traduzidas para as cores do arco-íris.
We try to adhere to a philosophy of colorizing the data that we call chromatic ordering.
So we're capturing these wavelengths in infrared light, and we're shifting them into the visible part of the spectrum. And we are assigning colors that represent shorter to longer wavelengths, just like we would see them.
Imaginem-no como uma canção tocada num piano, que é transposta para que a escutemos noutro tom. Contudo, continua a ser a mesma canção.
So the longest wavelength is going to be red, so I will make that red. The next longest wavelength, I'll assign that green, and then the shortest wavelength, and that'll be blue. And in this case, we actually have 4 filters. One of them is a narrowband filter that is really isolating a very specific kind of light, and that one we color orange. So after pulling everything together, I see the initial color composite image here, and it's really interesting. There's a lot of potential here, but I also see that it's very flat and it needs some compositional work.
And then this where it kind of goes into the subjective and more into the artistic.
The stars can look very different. The quality of the nebula can look very different. There isn't really like a hard point where it becomes, going from science to art. It's sort of the whole process. The science is always there. We're always respecting the data. We're not trying to introduce things that weren't there in the data to begin with, and we're not trying to remove things that are there. So the whole goal of this is to create an aesthetically pleasing image that will capture someone's attention and hopefully inspire them to want to learn more about this region in space.
Esta imagem da nebulosa da Tarântula não é apenas bela. O olho de infravermelhos do JWST revela milhares de estrelas bebés, outrora ocultas ao nosso olhar, dando aos investigadores novas pistas para a descodificação do ciclo de vida das estrelas.
You look at a newborn and you get a feeling for what that person will be when they are grown up, and the same thing for stars. You just measure them at the very beginning. You can imagine and you can infer how they will be and what they will become.
No Instituto de Tecnologia da Califórnia, uma equipa internacional de cientistas recebeu os seus dados do JWST.
We're just going to launch right into it.
Juntam-se para discutir e debater os resultados do seu teste do telescópio.
We have a great team. We have people in the US, we have people in Japan, we have people in Europe, we have young people and old people.
And then I was going to talk about...
So this group of astronomers I've known for many years since my graduate school days, and I would call them my family.
Team 74-6.
That's his favorite.
So for the last 2 years or so, it's been primarily meetings through Zoom, but there's no substitution for just the energy you get having people in a room together. It's fantastic.
A equipa reuniu-se para perceber o que lhes diz o JWST acerca de um dos mais misteriosos objetos do cosmos: os buracos negros supermassivos.
All all massive galaxies in the universe have a huge black hole at their center.
What do I love about black holes? So black holes are just the most amazing consequence of gravity.
A gravidade de buraco negro é tão extrema que o que quer que lá entre nunca mais sairá.
Not even light itself can escape from it.
Material is falling into it the whole time, and they have these big disks of dust and gas and everything, which is swirling around the outside, all trying to fall into the black hole.
But we don't know how they got there. We don't know how you make a supermassive black hole. We don't know how they formed.
So when we're thinking about these massive black holes at the centers of galaxies, a big question is sort of who's in charge? You know, is the host galaxy in control of the galaxy's evolution? Or is that big black hole at the center, is it having a really strong impact on how the galaxy changes over time?
Na verdade, parece haver uma estranha ligação entre buraco negro supermassivo e a galáxia que o rodeia.
Seems like the ratio for the black hole mass to the star mass is about 1 to 1,000. So that seems to imply that somehow the galaxy itself knows how massive the black hole is in it.
It doesn't make that much sense because the black hole, its sphere of influence is so small, it cannot really know what's around it. So how would those things be correlated? Why are they so correlated?
Keep in mind that we're talking about stars that are so far away from the black hole itself that the stars don't actually feel directly the gravitational influence of the black hole.
Uma das melhores formas de investigar esta estranha relação é estudar galáxias em fusão.
When you throw two galaxies together, you can potentially grow a supermassive black hole because you're now feeding it, you're giving it all this material because it's crashed into this other galaxy. And by studying merging galaxies, we can potentially understand better how these supermassive black holes grow. What sort of interaction does the supermassive black hole have with its surroundings?
You have both black holes that are feeding and star formation happening in these galaxies.
Toda essa atividade faz agitar tantas poeiras que é quase impossível ver o desenrolar da ação.
It's very hard to actually look and see a black hole because all this dust and gas is in the way.
E é aqui que entra o olho de infravermelhos do JWST.
So I went to grad school in Arizona, and every now and then a dust storm would blow through. And anyone who's ever been in a dust storm knows you can't see through dust. But infrared light has this amazing property that it allows us to peer through dust.
Esta é uma imagem captada pelo Telescópio Espacial Hubble, através de luz óptica de duas galáxias no processo de fusão. E este é o seu aspecto em luz infravermelha através do Telescópio Espacial Spitzer.
When you looked at it with Spitzer and infrared light, all of the energy was coming from that one region behind this shroud. And we knew we wanted to look at that.
Creem que algures no interior desta região está buraco negro em crescimento. Mas apesar de o Spitzer ter sido um dos telescópios de infravermelhos mais avançados do seu tempo, o seu espelho tinha apenas cerca de 85 centímetros de diâmetro em comparação com o espelho de 2,40 m do Hubble e com o gigantesco espelho de 6,60 m do JWST.
And so clearly Spitzer, resolution is fairly low, but if you go now to what we see with the new James Webb images, this is what we see when we have a 6-meter telescope in space.
Os espectroscópios do JWST conseguem ver através das poeiras, revelando estes 3 pontos distintos. 2 são aglomerados de formação de estrelas, e um deles é provavelmente buraco negro a alimentar-se.
So the final scenario is that now you could see exactly what is on that giant blob.
We previously just knew that something was lighting up the dust, but we didn't know what it was. We're now able to see, oh, there's a supermassive black hole in there. And not only that, but it's destroying the dust in its immediate vicinity.
It gives us a very close-up view of what's happening inside the galaxies, how the gas is getting into the supermassive black hole, what the supermassive black hole is doing to the surrounding area.
And so the fact that we can see it at that level of detail is what amazed me.
Há grandes esperanças de que nos anos vindouros este nível de detalhe sem precedentes forneça novas pistas sobre como ganhou forma esta relação entre os buracos negros supermassivos e as suas galáxias. É de manhã cedo na Universidade do Texas, em Austin, e esta equipa acaba de receber os seus dados e imagens do JWST.
Okay, it's recording.
O investigador principal, Steven Finkelstein, registra um diário em vídeo do trabalho da equipa.
Good. We've definitely had some highs and we've had some lows. Really exciting to see the data when it first came in.
Yeah. So this one looks really good. You've got something weird going on here where it doesn't look.
A equipa está a testar a capacidade do telescópio para detectar galáxias a muitos milhares de milhões de anos-luz de distância, para responder a uma pergunta que há décadas intriga os astrónomos. Como é que o universo ligou as suas luzes pela primeira vez?
When you think about the universe, it's sort of like we have this 13.8 billion year story. And we've put together a lot of the pieces of that story. We know a lot about it, but there's still these holes. There's these gaps in the story that we don't quite know the answers to. And one of the critical gaps is sort of the very first chapter of the story of the universe. We don't know how galaxies got started.
Se o universo tivesse um álbum de recordações, esta seria a sua mais antiga foto em bebê. A radiação cósmica de fundo em micro-ondas. O crepúsculo do Big Bang, quando o universo tinha apenas uns meros 378 mil anos de idade.
Has little dimples all over it that are really important to our history. Our calculation says that the little dimples correspond to variations of density. And that matters because, in our idea, the denser areas turn into objects like galaxies and stars and eventually planets and people. So we're here because there were dimples in the Big Bang.
Mas depois...
There's this missing piece. There's this that is hundreds of millions of years long.
Um tempo misterioso, conhecido como Idade das Trevas Cósmica.
The Dark Ages was a period of the universe's history for several 100 million years when stars themselves didn't exist.
You can sort of think of it as a hydrogen fog, mostly hydrogen. And when you have just hydrogen atoms floating around, the intervening light would sort of bounce off the hydrogen. And so you can't see through it. So we sort of refer to it as a fog.
Na fotografia seguinte, o universo já está na sua adolescência. E está bastante crescido. Aliás, está cheio de galáxias.
We have, if you want teenage pictures and beyond, we're missing the toddler images.
Falta-nos essa imagem de como terminou a Idade das Trevas e como se formaram as primeiras estrelas e galáxias. Uma página em branco na compreensão da nossa história cósmica. Uma página que muitos investigadores por todo o mundo, como a equipa de Austin, esperam conseguir preencher. A equipa passa uma semana a escrutinar os seus dados em busca de galáxias ancestrais.
So there were a group of us working here together looking at these very distant galaxies. We'd all gather around the computer and look at them and say, yes, that's a good one, yes, that's a good one, no, not that one.
Durante este processo, descobrem uma tênue mancha avermelhada.
When I first saw it, I don't believe it. It said redshift of 14. Redshift of 14 is about 290 million years after the Big Bang.
Estando correta, esta data significaria que o olho de infravermelhos do JWST está a ver mais para trás no tempo do que algum telescópio alguma vez viu.
One of the amazing things about telescopes is that they are literally time machines. They allow us to see the universe as it was in the distant past.
À medida que a luz viaja das galáxias ancestrais para os nossos telescópios, sofre uma incrível transformação de luz óptica a luz que conseguimos ver para a luz infravermelha.
What's happening in the universe is it's expanding and pulling space apart as it goes, and it's stretching the light in the same way.
Este estranho alongamento chama-se desvio para o vermelho. Quanto maior o desvio, mais antiga é a galáxia.
That's why the telescope was built, to find those distant, faint red galaxies, some of which are the first galaxies that formed after the Big Bang.
That looks pretty deep. Obviously, right?
Com base nas suas conclusões preliminares, a equipa acha que pode ter encontrado uma das galáxias mais antigas alguma vez vista por humanos.
We've spent the last 24 hours trying to throw everything we can at this galaxy to convince ourselves that it is not an extremely distant galaxy, and we failed. So with that, it's my daughter's birthday. I'm gonna go take her to dinner and then spend all day tomorrow trying to write up this paper draft and hopefully get it out there pretty soon.
A equipa chama a galáxia Maisie, o nome da filha de 9 anos de Stephen. Mas a descoberta da Maisie não foi a maior surpresa.
We were able to see right away there were lots of really distant galaxies to find, and every time we made the data better, they just got more believable. Oh, there's still more.
Yeah, there's so many. We were giddy. We were little school children, looking at all these galaxies and all of these images.
Na verdade, a Maisie é apenas uma de muitas galáxias ancestrais que podem ser vistas neste assombroso mosaico de imagens do JWST.
Galaxies, galaxies, galaxies. The full image has about 100,000 galaxies.
You hardly find any empty spaces in the images. Every tiny little speck, every space is a galaxy, and you zoom in and you see more, and you zoom in and you see more.
And so this was Maisie's galaxy, this little red blob right here. Beautiful red blob right here.
There's a lot of excitement, there's a lot of early preliminary results. That's the scientific process, where people are finding candidates to be some of these very distant galaxies and then studying their properties.
Para já, a Maisie é considerada apenas uma candidata, porque a sua idade é ainda incerta, enquanto o telescópio está a ser calibrado.
It is really important to get the calibration of your telescope right, because when you take an image of a galaxy or a star, basically the only thing that you're measuring, the fundamental measurement, is the brightness of that object at different wavelengths. And so you need to get that brightness right.
O que é exatamente o que uma equipa do Instituto Científico do Telescópio Espacial está a tentar fazer. O que descobrirem será crucial para o futuro do JWST e para a fiabilidade de todas as descobertas obtidas a partir dos seus dados, incluindo a idade de galáxias ancestrais, como a Maisie. A equipa está a observar um aglomerado estelar conhecido por Messier 92, um dos mais brilhantes e antigos conjuntos de estrelas da Via Láctea.
These are stars that have been studied for decades by lots of telescopes everywhere, and we know a lot about them.
Mas quando recebem os seus dados do JWST,
I think I found an error in the way I'm
algo está errado.
When we were looking at the data for the first time, what we were seeing was that the brightness of stars measured on the different detectors was a little bit different on each detector. So one detector was measuring a star a little bit brighter, the other one was measuring a little bit fainter.
Is this the M92 image that's weird? Yeah.
O astrofísico Hakim Olushey demonstra a discrepância que encontraram usando fotómetros e esta lâmpada de 100 watts.
Assume that this light bulb is my star that has been measured over and over and over again for decades, and I know how bright it is, really. And now I have a detector that I'm gonna point at it, and it's gonna give me a reading for how bright this light is. So I point this at my star, and then I lock in the measured value. Now I'm gonna take a different detector, and I'm gonna do the same thing. And I do that with another detector. Hold it for the standard distance and lock in the value. Well, guess what? They don't all have the same reading. They are slightly different one from the other, and that's normal. If I took the light from a single star and shined it on different detectors, they may each give us a different reading.
É um problema comum que o cientista de instrumentos Mike Ressler conhece muito bem. Ressler ajudou a desenvolver os detectores para um dos instrumentos a bordo do JWST, chamado MIRI.
The detectors we use in MIRI are silicon detectors, and they are very similar to the detectors that you might find in a digital camera.
Aliás, se retirarmos a lente, encontraremos um detetor atrás do obturador, este chip de silício retangular esverdeado.
The light comes through the lens and gets focused on that rectangle, and that is the detector. Each detector has its own personality. So one detector might be a little bit more sensitive than another. They don't all respond to light in the same way.
O MIRI tem 3 detectores como este. A bordo do JWST estão 18, cada um com a sua personalidade.
We're trying to ensure that the personality of the detector doesn't show up in our data. We want the data to represent what's actually out in the universe.
Usando a luminosidade conhecida das estrelas do Messier 92 como guia, a equipa ajusta a forma como processa os dados, atualizando a calibração do telescópio.
Once we've calibrated our instrument, we can go and point it at things that we have no idea how bright they are intrinsically. And by measuring its brightness, we can now get a very accurate measurement of its distance. And those are the numbers that go into our calculations of the evolution of the universe.
Em Austin, a equipa também está a melhorar a forma como processa os seus dados. Isto, juntamente com ajustes na calibração dos instrumentos, vai modificar a estimativa acerca da idade da Maisie.
The distance did change over time in the first few weeks as we understood the data. That revised the distance estimate from a time about 300 million years after the Big Bang to about 370 million years after the Big Bang.
A Maisie está provavelmente fora da corrida para a galáxia mais antiga alguma vez observada.
There's sort of a game in the field of trying to find the record holder, right? Because it's exciting and everybody wants the most distant one. And that's fun, but I think the real science is going to come from studying their properties in more detail. What their colors are, what their shapes are, what the properties of their stars are. And that's scientifically a lot more interesting than just the record holder.
O telescópio tem explorado o cosmos 24 horas por dia. Os investigadores de exoplanetas Kevin Stevenson e David Singh estão prestes a receber os dados do que pode ser uma das observações mais difíceis até à data. Tentar detectar a atmosfera de um exoplaneta rochoso, algo que nunca foi feito por qualquer outro telescópio. Concentram-se num exoplaneta chamado GJ486b. Os investigadores calculam que seja 30% maior do que a Terra, mas em comparação com Júpiter ou com um gigante gasoso como o WASP-39b, é simplesmente insignificante, o que torna a sua atmosfera muito mais difícil de detectar. Por isso, com todos os planetas rochosos que existem por aí, por que escolher este?
It's only about 26 light years away, so it's very close, just in our own neighborhood.
Tendo em conta o tamanho do Universo, fica praticamente na porta ao lado. Este planeta também tem uma órbita próxima em torno de uma anã vermelha, uma estrela mais pequena e ténue do que o nosso Sol.
When we want to study rocky planets that are Earth-sized, we cannot change the size of the planet. So our goal is to go after those rocky planets that are around the smallest stars.
So it's one of the few select planets you have a chance to see an atmosphere around a rocky planet. Alrighty, let's get this party started and look at the second transit.
O JWST registrou um trânsito. Agora começa a busca por uma atmosfera. Passam dias a analisar as suas observações, cada um usando métodos ligeiramente diferentes para processar os dados. Os resultados de Kevin parecem promissores.
There's a lot to look into to make sure that the result is robust. But at this point, maybe. That would be cool.
O seu próximo passo será reunirem-se com os seus colegas de equipa para compararem resultados.
Everyone excited?
Oh yeah.
Excellent. Okay. Well, let's take a look at the transmission spectrum.
Verifica-se que quando David processou os dados, não encontrou a assinatura química de uma atmosfera.
So one possibility is it doesn't have any atmosphere, and the spectrum would look basically just like a flat line. So there's a lot of talk about, is it a flat line? Is it not a flat line?
Uma linha reta, porque a assinatura química da luz da estrela não pareceu mudar quando o planeta passou à sua frente.
Okay, now let's look at Kevin's. We've got it looking inconsistent with a flat line at first blush.
Kevin detectou uma pequena variação.
This one is pretty consistent with water. Wow. Yeah.
Água poderá significar que este mundo rochoso tem uma atmosfera.
Well, I think an atmosphere is still on the table. I mean, if I bet right now, I think it would probably be a flat line, but it's close.
Serão necessários meses e mais observações para determinar a existência de uma atmosfera no GJ 486b.
We are on the bloody edge of like what this telescope can do. We are on the very edge of what the instrument capabilities are, the telescope precision, and we are hoping that we can tease out signals that are on the order of tens of parts per million. We don't know the answer yet, but we also can't say that the transmission spectrum is flat. And so there's optimism.
I would say cautiously optimistic.
No que toca à busca pelos pilares químicos da vida no nosso próprio sistema solar, as observações do JWST de Encélado e de Europa finalmente chegaram.
I was wondering about this, by the way.
E os investigadores começaram a analisar os dados, pixel a pixel, criando mapas químicos de dois mundos misteriosos. No que toca às plumas de Encélado, encontram algo absolutamente bizarro.
We saw this huge plume which stands at 40 times the size of the moon.
Para colocar isto em perspectiva, este pixel vermelho representa o tamanho de Encélado.
The moon is within a pixel. A pixel is actually bigger than the moon.
Os pixels azuis à volta são água, que jorra das plumas.
This cannot be right. This is too big compared to the moon.
E esta gigantesca pluma pode estar repleta de indícios dos pilares químicos da vida no seu oceano subterrâneo.
You can look for carbon dioxide, carbon monoxide. For every single pixel that we actually had a full spectrum behind it.
Europa também traz uma surpresa. Afinal, a sua superfície é muito mais complexa do que a equipa esperava.
So this is on the surface?
This is on the surface. We're seeing all this surface composition, speaking to us. I mean, and we have a spectra for every single of these pixels, so we can actually see what it's made of. So I think this data is going to be super cool. We're seeing things on the surface that never seen before. We can see the ices changing and new ices, signatures that we were not expecting. You just have to go and mine it and search for it. If you don't search for it, you don't know. So our exploration has been just slowly going molecule by molecule, but there are hundreds of other molecules or ices that may be hidden behind every pixel.
Jerónimo Villanueva e a sua equipa dedicarão os próximos meses ao estudo desses pixels, procurando os pilares químicos da vida em Europa e em Encélado. Em Austin, a equipa recebeu novos dados, desta feita provenientes dos espectroscópios do JWST.
The spectra tell us about the chemistry. It tells us about the physics. It tells us how many heavy elements have built up. It can tell us what the age is. It can tell us what the rate at which the galaxy is forming stars. And so all of the really important physical information really comes from the spectra.
E os espectros estão repletos do inesperado.
One of the things that really strikes me about looking at the spectra of these high redshift galaxies is how much detail we see. In these data that we're just getting, we're seeing signatures of heavier elements, even for very high redshift galaxies.
So you're seeing oxygen emission here. We're also finding hydrogen lines, we're finding neon. So this is all kinds of detailed information about galaxies in the first, 500 million years that we've never, ever had before. And so we're not just finding these galaxies in images, we're actually characterizing them for the first time. And so this is really exciting and revolutionary.
Mas também gera mais perguntas do que respostas. A detecção destes elementos pesados em galáxias tão antigas significa que o universo pode ter ligado as suas luzes muito mais depressa do que o que tinha sido previsto.
So both the fact that we're seeing a lot of high redshift, massive galaxies, and the fact that we're seeing chemically enriched galaxies at this time period gives us a bit of a mystery. So why is it that stars would have either formed earlier in the universe than we thought or formed more rapidly, right? Something about that process of star formation is more efficient, is happening, more rapidly than we initially might have guessed.
We had models of how the first galaxies form, how long it takes, what they look like, and James Webb Space Telescope completely blew these models apart, right? We found that our models, they were a little slow in comparison to nature.
The fact that we're finding more than what most models predict means there's something about those models that's incorrect. And so I think the models of how these galaxies form in the early universe are going to have to change to actually match the observations now.
Com cada novo telescópio, a nossa imagem do universo torna-se mais nítida.
When you have new eyes, you discover new things. And that's exactly what's happening here. It's almost like discovering a new land, discovering a new planet. With Webb, we're discovering a new universe.
O primeiro capítulo de exploração do JWST demonstrou o quão revolucionário este pode ser.
It's surprising every single time we point this telescope at something new. It hasn't really failed us yet. JWST is doing exactly what we thought it would, and more.
I know that we've built a telescope that is still more capable, and we're just tapping into those abilities. And so I think the next couple years are going to be tremendous, and that we really haven't seen anything yet.